And thank you everyone for coming to this session. We'll be talking about how DeepSeek's flash multi-head latent attention speeds up transformer inference. And if you attended the keynote right before this, they talked all about what attention is. We'll be talking about how to speed it up on GPUs. So this is the agenda for today. I'll introduce attention, just a recap, and talk about what are the bottlenecks in computation when it comes to the attention algorithm. Next, we'll talk about how we can go from attention to latent attention. This was the algorithmic innovation that DeepSeek introduced. Next, we'll talk about I/O-aware algorithms. So I/O-aware algorithms means they know about how the hardware and GPUs is organized, and they utilize that in their implementation. Then we'll talk about an I/O-aware algorithm on GPUs, flash attention, which was the first to really speed up the attention implementation on GPUs. And then lastly, we will talk about FlashMLA, which is what we are here for. So let's start with attention. This is the original transformer architecture with the encoder-decoder setup as it was introduced in 2017. Attention is all you need. Since then, there have been minor changes in how things are done. We don't use the encoder as much. We use the decoder-only models more. We don't apply the norm after the attention layers. But besides these small changes, the overall transformer architecture has remained quite consistent, I would say. So the main contribution of this model was our multi-head attention layer. So in multi-head attention, each input token is embedded through a linear layer into the query key and value vectors. And corresponding to different heads, there are multiple vectors for each token. We then apply scaled dot product attention, concatenate our outputs from SDPA, scale dot product attention, and then pass it through a projection layer, get our final outputs. So this is multi-head attention. And the scale dot product attention, as it was in the original paper, is shown here, but we'll expand into it. So let's take a closer look at scale dot product attention. So it's the same figure from before. I just added some dimensions here so as to visualize certain things. So the representations for the keys, queries, and values, they are usually of the size sequence length, which is how many tokens our model has seen, times a certain embedding dimension. So embedding dimension or head dimension, sometimes it's called, can be of order of like hundreds or tens. So like 64, 256 are common ones. But the sequence length, and this is key here, corresponds to how long of an input the transformer has seen. And sequence length can be of the order of thousands, hundreds of thousands, even millions. And we want to scale to longer sequence lengths because it's been shown that the more context your transformer has, the better it is at reasoning in images, like dealing with high resolution images. So it works better. Now in this entire operation, you'll notice that the QK transpose matrix, the score matrix, and the attention matrix are the only ones that are of a size n square in the sequence length. All the others are n times d or d times n. So what does this lead to when we compute attention? So you'll notice that with each query token, with each new token that we are generating, the attention matrix grows by a size of O of n square. And this proves to be a bottleneck. If we are dealing with like context lengths of millions, we are talking about a matrix which is of the size like million times million. So at each step, we are doing a lot of computation. But do we need all this computation at every step? Let's consider the masked attention matrix on the right side. You'll notice that only the bottom triangular half is being calculated. The upper triangular half is not being calculated. Why is that? Because when we are generating in an autoregressive manner, we don't care about the queries that will come in the future. We only care about the queries that came in the past. So really, at any point, what we really care about is that one row of our attention matrix when we are decoding. So we could potentially trade off compute for memory. And this is where KV caching comes in. So instead of performing the full matrix multiplication for every query token, what we can do is we can save our keys and values as we see them in a cache. And at any point, we multiply a single query token with the key cache to generate our row of the attention matrix. and then we multiply that row by the value cache to generate our output token for that time instance. So what did we do? We traded off compute for memory. Instead of doing an n square computation, we are doing an O of n computation, but we are saving an extra O of n in memory for our KV cache. So KV caching is great, but the memory costs can add up. So for the DeepSeek V2 model, if we were to store floating point 16 activations for the full KV cache, for each token, the KV cache will be 4 megabytes in size. And the context length for this model was 128,000. So the full KV cache for the entire model ends up being 512 GBs. And there's no GPU available today that's that big. So biggest GPUs you have is like 80 GB in memory. And this is just the KV cache. We are not even considering the model, the data, or anything. So clearly, this is not possible. So how do we solve it? And this is where latent attention comes in. So in the past, there was already a lot of research on reducing the size of the KV cache. I'll skip over some of this, but in summary, the idea was you could reduce the representation size of your network, and as a result, you could reduce how much KV cache you save. So for each attention head, instead of having a full KNV cache, you could maybe just have one cache for all the heads. This is multi-query. Or you could have grouped together caches for a few heads. This is group query. And while these are great, like they lead to reduction in sizes, like 20x times for each. What they are bad at is they are just reducing our representation capacity. So our model cannot express as much, and as a result, the model performance suffers. Now, what if we could have the best of both? What if we could have low size and we could have high performance? And this is what multi-head latent attention, MLA, achieves in practice. So how does it do that? Let's look at the KV cache again. So what we are doing is just projecting with a matrix our input to the K and the V matrices. Now, matrix projection in machine learning has been often broken down into a down projection followed by an up projection and has worked excellently in multiple different domains. So those of you from NLP have seen LoRa, low rank adaptation for fine tuning, works great. Those of you from computer vision like me might remember inception networks where we have factorized convolutions. First, we do a down projection, followed by an up projection. This is just showing it for our KVE matrices. We are now down projecting to a small latent matrix and then up projecting it to our KV matrices. So let's put it back in our attention picture. Now, instead of generating the K and the V directly from the inputs, we first down project using WDKV, then we up project. And the nice thing about having this latent representation is now performance is not lost because we are then up projecting it further. Of course, the paper has multiple different innovations, so it's hard to isolate how much of the performance gain just comes from this. But in practice, it performs almost as well as the full KV cache. A bunch of math here, but in summary, like for the full DeepSeek V2 model, if we were to save the MLA versus the MHA, the KV cache ratio is almost 50 times smaller. And this is a side note about the implementation of how MLA is implemented. Instead of doing the up projections, what DeepSeek did was they absorbed the up projection matrices into the query projection and the output projection. So before the yellow embeddings and after the red embeddings, as you can see there. Mathematically, it comes out to be equivalent. And the reason they did this was that by doing this absorption trick, now, if you look at just the operations, the arrows and the matrices, now the operations in MLA, in terms of what your GPU sees, are exactly the same as the operations in attention. So why do that? So attention has already been studied, already been implemented on GPUs. So if you could use the same computations as attention, then you can utilize the same optimizations that are done in attention. So what are these optimizations? Before we talk about what are these optimizations, let's talk a bit about how algorithms are implemented on hardware. Let's take a look at this naive picture of attention. We have our GPU memory and our GPU cores. We are loading the query and key matrix, computing our score, writing it back to memory, loading our score, computing our attention weights, writing it back to memory, loading attention weights and values from memory, computing final outputs, writing it back to memory. So what is hiding in plain sight here? Any guesses? What's hiding is memory I/O costs, and we never consider this when we are talking about algorithms in theory. There's a big cost in reading and writing these large matrices. So for some background, the computational capacity of GPUs has been increasing at a much faster rate than their memory bandwidths. And this is not going to change anytime soon. You're not going to suddenly want bigger chips. There's physical restrictions on memory bandwidth speeds. Your chip will need to draw more power. It will need to dissipate more heat. So this trend will hold. And what this leads to is that there are now two unique bottlenecks when you're implementing an algorithm in memory. So there's compute bound, where if you had more cores, your algorithm would just magically run faster if you were able to get more cores. But now there's also a memory bound regime. And in memory bound, what's happening is that there are more cores, more compute available, but your algorithm needs so much data that your memory bandwidth is now proving to be a bottleneck. You are not reading memory fast enough to use up all those cores. And in hardware, another important concept is that of Amdahl's law. So what that states is that overall performance improvement gained by optimizing a single part of your algorithm, a single part of your system, is limited by the time spent doing that part of your algorithm. So for example, if your algorithm spends 25% of its time doing part A, even if you were to 100x the performance of part A, you'll only get a 33% speed up in your algorithm. Whereas if you were to 100x part B, which is taking 75% time of your algorithm, you'll get a 3 times speed up. So there's a bitter lesson from Amdahl's law. In attention, the matrix multiplication operations, the QK transpose and then the attention times value, they take up most of the operations that are being performed, almost 100%, 99.8. And these are very fast on GPUs. But the other operations, the softmax, the mask, the dropout, even though they make up very little flops, they are so much slower that they end up being the bottleneck in your attention runtime. And the runtime breakdown is shown on the left from the flash attention paper. You can see they're coming to dominate the runtime despite being very little of the flops. So enter flash attention. So flash attention solves this, and we'll see how it solves this. It reduces the GPU runtime of attention by 3 to 4 times. So the key insight is GPU memory is not monolithic. So if you have your system, for example, you have your CPU memory. In servers, this could be 1 terabyte or even more. But its memory bandwidth is very slow, of the order of tens of GBs per second. Then you have your GPU memory, which we think of as CUDA memory. This could be 40 GB, 80 GB. And this has a bandwidth of 1.5 terabytes per second. But in your GPUs, the way they work is they have multiple processors. Here is shown as SM. In CUDA GPUs, they are called streaming multiprocessors, SMs. And each processor has its own small SRAM. And the SRAM for A100 has a memory bandwidth of 19 terabytes per second, so almost 10 times that of the GPU RAM. Now, what's the catch? The closer your memory is to compute, the smaller it tends to be, simply because of physical restrictions that I mentioned before. So how can we exploit this hierarchy in memory? And this is what flash attention does. If we were able to break down our computation in such a way that everything that we need to compute on will fit in the small SRAM, then we can perform 10 times more operations before we are bottlenecked by memory. So this is a very common approach used in GPU algorithms. It's called tiling. You break down your entire data into small tiles, read small tiles into the smaller SRAM, perform all computations on the data, and only then you load your next data. So this way you are like not being bottlenecked by memory by up to 10 times as many operations. However, in the actual math for attention, you need to compute the softmax. So for the softmax, you need the full row of this QK transpose matrix to normalize. And the innovation that the flash attention authors used, this was previously known, is they calculated the softmax in an online fashion. So they maintained some running statistics about what's the maximum, what's the average for each tile. And then at the end, when they're writing out the outputs, when they're doing the normalization, they utilize these running statistics to calculate our softmax. And a very brief note on GPU programming. I don't expect you to become a CUDA expert after this, but The compute hierarchy in GPUs has a corresponding programming hierarchy in the programming primitives. So we saw a kernel is just a GPU program. It runs on the full GPU. And then for each streaming microprocessor, there are blocks. They are just groups of threads that run together. And then for each single core in the processor, we have a corresponding CUDA thread. So when we saw those tiles that were being operated on, I showed them sequentially, but the way that it's working is like a lot of the threads are running them in parallel. So they are also utilizing lots of memory resharing when they are doing these tiling operations, because the same tile is being used for many different threads. And this is a side note, this is not related to inference, but another innovation that Flash Attention did. In the backward pass, you need the full attention matrix to calculate the gradients. But we never instantiated the full attention matrix. But as I mentioned before, compute is much more available than memory bandwidth. So in the backward pass, they just recompute the attention matrix. And this adds a lot of flops to our algorithm. It adds like 1.12x more flops. But the backward pass ends up being 7 times faster due to this. Pretty incredible. Okay, so this is a great summary picture of Flash Attention from Hugging Face. You're loading tiles of the keys and values matrices. Then you're loading tiles of your score matrices, the running statistics that I mentioned. And instead of reading and writing data back and forth doing operations, you do all the operations on the tiles, and only then you write back the data to memory. So this is in GPU programming sometimes called kernel fusion. Instead of doing multiple operations, you have one kernel doing all the operations on the data that's in SRAM. Okay, so Flash Attention is great. Why do we need FlashMLA? So Flash Attention is optimal for A100s, the Ampere generation of NVIDIA GPUs, achieves around 80% flops utilization. However, on the newer generations, such as Hopper, it achieves a 35 to 40% of the theoretical flop utilization. So why is that? And this is what FlashMLA solves, and we'll get to it now. So newer generation of GPUs have something called tensor cores. So what are tensor cores? Tensor cores are dedicated hardware units for performing matrix multiplications. And in the image that I'm showing here, on the left, you have a matrix multiplication being done by a CUDA core. And on the right, you have a matrix multiplication being done by tensor cores. So the nice thing about tensor cores is that they are loading memory in arrays directly. So they are loading entire matrices in one GPU clock cycle. And they are optimized to only perform matrix multiply accumulate. They don't perform any other operation. So as a result, they can do it much faster. This is from an older generation, Pascal and Volta, but the newer generations are even faster at doing mathmul. So the FlashMLA algorithm is for the Hopper architecture generation. And the Hopper, I think, has like I would say 100x order more throughput for mathmuls than Volta. So how do tensor cores do matrix multiplication that fast? So for the Hopper tensor cores, they have 2 unique instructions that are used. So the first instruction, and this is a dedicated hardware unit as well, TMA, Tensor Memory Accumulator. And you can just remember this as matrix copies. So TMAs copy entire matrices from our GPU RAM to our SRAM very fast. And the way they do it very fast is they don't have to calculate, oh, what index of the tile do we need to load? Sorry, you don't have to calculate it. The TMA will do it for you. And the other thing they do is warp group MMA. So you can think of this as just matrix multiplies or batched matrix multiplies. So we use multiple threads. We call it a warp group. It could be 128 threads in the Hopper GPUs. We use 128 threads to perform matrix multiplication on matrices of size, say, 128 times 192, or it could be some other sizes. And it's fixed what sizes of matrix you can operate on, but as a result, the throughput of this matrix multiply is very high. So theoretically, for the Hopper GPUs, the tensor cores have like 15 to 20 times the throughput of CUDA cores. And a note here, like the DeepSeek authors used H800, which is a throttled version of H100s. Due to export restrictions, H100s are not shipped to China. But it still has a peak tensor core T-flops of around 865. Okay, so tensor cores are very fast. we want to maximize tensor core usage in our attention computation. So the way FlashMLA, the algorithm that the DeepSeek authors introduced, does it, it has two warp groups, so two groups of 128 threads running in parallel. And we'll see why it's important to have two warp groups in a second. And they split our attention computation vertically, so the output matrix that we are calculating, they split it vertically. And they perform operations on each half of the output alternatively. And the reason it's important to perform half of the operations in one warp group, half in the other, is because you also want to make sure that the time you spend loading your memory does not bottleneck the time that you are doing your computation. So while one warp group is doing the matrix multiplication, the other warp group can schedule the next memory load that needs to happen. And these schedules are async. So as soon as the previous operation is done, as soon as the tensor cores are free and we don't need that memory, the next part of the matrix, the next half gets loaded and can be operated on. So as you can see, like between each of the barriers with the dotted lines, at any time, the tensor cores are running. So like we are maximizing the tensor core usage. So we are overlapping memory load with matrix multiplies. Okay, so this is a recap of what I said earlier. Tensor cores are much faster than CUDA cores. So another thing we would want to overlap is tensor core operations with CUDA core operations. So this is, again, where the two warp groups come in handy. And this is common in systems programming. This is called a producer-consumer approach. Like one thread or one warp group in this case produces something, example, loads memory or performs a matrix operation, and the other consumes what has been done by it before. So for example, if one loaded memory, the other will operate on that memory. If one already operated on that memory, the other will maybe use up that memory or perform a different operation. So now we are overlapping tensor cores with memory loads. We are also overlapping tensor cores with the other operations, the CUDA operations, so scaling, softmax, and so on. So as you can see, while one warp group is busy doing the matrix multiplies, the other warp group can perform those scaling softmax on the data that's already ready. So again, this shows why we had to split our computation into two halves. Now half of the data is ready. We can do the next operations while the other half is being operated on. Great. So this is the summary of the FlashMLA algorithm. It's an algorithm for efficient calculation of attention on the Hopper GPUs that uses tensor cores, and it achieves 80% flop utilization. The scheduling that is introduced here, the authors call it a seesaw schedule because you're seesawing between CUDA cores, tensor cores, seesawing between tensor cores and memory loads. And 80% is about as good as you can get when you have multiple different operations happening in any algorithm. Okay, to summarize. So the attention matrix computation is O of n square in sequence length. For longer sequences, this proves to be a bottleneck. So we trade off compute with memory. We store O of n KV caches in memory. And MLA, multi-head latent attention, replaces our KV cache with a latent KV cache to reduce the size of our KV cache. And on hardware, on GPUs, memory I/O can be proved to be a bigger bottleneck than the actual compute. So we have to be careful about memory I/O. And flash attention solves the memory I/O problem in attention by loading tiles or blocks of data, performing all operations on those tiles, and writing them back. And in order to calculate the softmax, it does it in an online manner. And lastly, FlashMLA uses tensor core and overlaps tensor core matrix multiplies memory loads and GPU operations so as to completely utilize whatever flops it has available. So these are the references, the papers themselves, the Colfax research blog and GPU mode Discord server are great to learn about GPUs and CUDA. And that's the end of my talk. Thank you for your attention, and I'll take questions now.
Thank you so much for the insightful talk. We truly appreciate you sharing your expertise with us. I'm going to see if there's any questions. We have time for one question, maybe.
Thank you for the very interesting presentation. So I just wanted to ask regarding Triton. I see that it's becoming really popular to optimize every layer or every like fuse,
Yeah.
But I don't see that like, you switch like in your implementation for MLA attention, you were switching between, I don't know, tensor cores to CUDA operations and so on. And I have never seen in the Triton kernel like that is,
so
that granularity. Are we able to get that through Triton or higher level?
So that's a great question. Triton, for those of you not familiar, is like a Python-like language for programming GPUs. And it's being very actively developed, started from OpenAI, but a lot of contributions from Meta AI and NVIDIA. So Triton lags a bit behind, I would say, in terms of CUDA C++, but it's catching up very fast. So the two instructions that you saw that are being used, the WGMMA and the TMA, so it just added the support for WGMMA like a month or two ago, and the TMA is also on the roadmap. So it will catch up. It's just a little bit behind CUDA C++. And I would say, like, if you are in machine learning, it's probably easier to learn Triton than to learn CUDA C++.
So thanks a lot. It was really great. My question is about the arithmetic intensity of the, let's say, FlashMLA or just MLA when you compare to the flash attention.
So for the Hopper GPUs, it's like almost twice as much, because the flash attention, it did not use the Hopper GPUs, it did not use tensor cores, because it came out like earlier. It came out 2022, 2023, when Hopper GPUs were not even a thing. It is about 2 times as much more, but the flash attention authors also introduced a follow-up. It's called Flash Attention 3, which does use tensor cores, and it's about the same for Flash Attention 3 versus FlashMLA, except that FlashMLA is for the multi-head latent attention, not just pure attention.
Are you talking about the arithmetic intensity?
Yeah, like the flops used versus the memory IO, right?
So basically, you are saying that the V3 is equal to V2, and V2 is twice V1, right?
No, V3 is twice V2. V1 and V2 are pretty much the same. They were just like small optimizations. V3 and FlashMLA are kind of comparable, I would say, yeah.